Hey everyone, this is Ayush. I hope you're doing awesome. So today we are going to discuss about Code Gems Farewell Round A. So this video is quite late because this round happened between my NSEMs. But I still managed to give this contest and secure a global rank of 781. I won't say this is a really good rank because this was easy round. It was supposed to be easy because it is round A. I think I wasted too much time between problems doing random things. That explains my bad rank. But I finished the contest in 2.5 hours. If I did it better, I would have finished it in around at least like one hour 45 minutes, something like that. So yeah, so let's move on discussing problems. If you count, there were only three good problems in the entire round. So that there were total of five problems, and three of them were good. So that we are only going to discuss them. The first of the three good problems is the second problem. So this I won't say this was a tough problem, but this was weird. I don't know why I took these many attempts to AC it. Like I had the logic in the first attempt, but I think I was doing something wrong in the implementation maybe. So I would suggest to pause this video and read the problem statement. And yeah, I'll quick explain the problem statement with this example. So so in this question, basically you are given a road of length n, which starts from 0 up until n in units of 1, and you are also given like q bulbs, each of width, uh, each of same width, equal width, and like in this example it is three bulbs with three width, and you need to arrange them in such a way that you require minimum number of bulbs to lighten up the entire road. So you cannot rearrange the bulb because their position is given in the problem. So the like in this case, the first bulb is at the second position, and the second bulb is at seventh position, and the third bulb is at ninth position. So you need to find the minimum number of bulbs, so that will lighten up the entire road. So you need to count the minimum. You need to take a subset of this array, which lighten up the entire road. So like in this example, the first bulb is at second, of width 3, like total width would be 2 into the given width, so it will be 6. So you can observe that you only require the first two bulbs to lighten up the entire road. The third bulb is not required. You need to find the minimum number of bulbs that will be sufficient to lighten up the entire road. So like in this example, it is 3. In the second example, it is you will find out it is impossible to lighten up the entire road because there are no light in the second and fifth position, because the first bulb is before 4, and the second bulb is after 5. So this is impossible, but it is possible in third example. So the minimum number of bulb required in third example is 4. As you can see here, all of them are required. So yeah, so maybe you should pause again and think about a solution. But yeah, I hope you have thought about it, and let's move on to the solution. So if you think about it, you can solve this problem greatly. So you can just let's type something. So you can maintain a variable current. So this is basically the current last position on the road that is lighten up using the minimum number of street lights before it. So like in this example, suppose you can lighten up so suppose the current is 5, so you need only one bulb to lighten up the space between 0 and 5. So your current will be 5 here. So now let's write a transition. So the transition. So for next bulb, you can observe that you will always need a bulb whose starting position is before the ending position of the last bulb. So you can just put the entire you can just put the starting position of each bulb in a in a set. Like in Java, you can put them in a preset, which will sort them on the basis of their starting position, and calculate the starting position of a bulb that is closest to the current, and you can write base cases about it. And if it is before, if you cannot find a bulb that fulfills those conditions, then the answer would be no, and else it would be Yes, else it would be yes, and you can print the minimum number of bulbs required. So let's move on to the code, and let's see. So this was the code. It is quite messy. I could have written it better, but yeah, like let's just see it. So I have inputted here the all the things like the positions of bulb, number of bulbs, and all. So I'm going to maintain a set. This set this is a tree set that will store the first position or the beginning position of each bulb of each street light. So yeah, so we are storing it here, and we are going to maintain answer. This will store the minimum number of bulbs, and yeah, this flag will represent if the answer exists or it doesn't. So let's just start it with writing base case. So if like the first bulb is not starting from 0 or beyond, then you can say that the answer will always be false, because you cannot light the first places like zero from zeros. So suppose the first bulb starts from here, then the prefix from 0 to 1 will always be in dark. So you cannot the answer will always be no. So we have done flag is equals to false, and yeah, so now we'll move on to the next phase. So now we are going to maintain a current variable. This is the same variable I was talking about in here. So the last position of the road, that is lightened up using the minimum number of street light before it. So yeah, so you can just traverse the entire array, and with the conditions, and think and write some test cases. Let me just pause it. So let's just resume the video. Someone disturbed me there. So we were discussing the first problem implementation. So yeah, so we were going to traverse the array based on the not the array, like tree set, which is basically the first position of each bulb, and with this pointer known as current, which is the last position of currently lightened up road. So we're going to discuss it. We are going to traverse it up until the last position of the road, and yeah, so this is the first base case when the current is already present in the tree set. So if this how can I remove this? So yeah, this is our current position, and we want to find the next starting position that is before this but closest to it. So we are going we want to find suppose these are the two bulbs. So we will take this bulb, like this bulb, instead of this bulb, because this is closest to the current, and this will give us the minimum answer. And yeah, so this first test case is when the current is already present in the tree set. So when this position is already present in the tree set, that means that there is another bulb that starts at this position where the last bulb ended. So we were definitely going to take that. So yeah, so we'll update current by 2r, because each bulb is of width 2r, and move to the next position. Else we will find the lower value. So if there is no bulb that is lower, if there is no bulb that is lower to the current position, then the answer is going to be false, and we are going to print that. Else we will take the lowest value. This is the bulb whose this is bulb. Why can I spell bulb? Whose starting position is before the current but closest to it. So we can do this by lower function in the tree set. And like here's another base case. This is basically when your this is your current position, and this is basically when your the previous bulb, like the bulb we are going to take now, whose ending position lies before this current. So in this case we cannot move further, because there is no bulb out there, and we cannot lighten up this post fixed space. So it is not possible to lighten up the road. So in this case we are going to print the answer as false. So yeah, and at the end, if the current is less than m is basically the ending position of the road, so the answer will again be not possible, and we'll print it. And yeah, that's pretty much it about the second problem. Let's just yeah, there's the second problem. That's pretty much it about the second problem. I wouldn't say it is very difficult, but it took me a while to solve it. I don't know why, but yeah, it was a decent problem. Let's move on to the next problem. The last two problems were quite interesting, especially the second last problem. This was also a standard binary search problem. Yeah. So you should probably pause the video and read the entire problem statement, and I will also explain it to you quickly. So so basically in this problem you are given, so there's a big sequence of alphabets. So let's take this example. So let's move into the doc and discuss this problem. So this problem, what is the name of this problem? This is ASCII Art. So basically, you are here given a string of alphabets in the order A, B, C, D, E, F, G up until Z, and this sequence is going to repeat again, but this time each alphabet will be repeated twice. So AA, BB, CC, DD, EE, FF, GG up until ZZ, and again, like this time they will repeat thrice, like AAA, BBB, CCC, DDD up until ZZZ. So as you can see in the ith iteration, the each alphabet is going to be repeated ith time. So you need, and in the problem you are basically given like a random variable known as n, and you need to find the character in this sequence at the nth position. So yeah, this was the problem. So like in this case, this is like this is the sequence, and you need to find the fifth character. So it turns out it is E, and you need to find in second test case you need to find the 31st position character. So it is C. Excuse me. So you have to print these positions as asked, and yeah. So you should again pause the video and think about it. I'm also going to discuss the solution. Hey, so Hey, so I hope you paused the video and thought about the solution because I did. So let's move on to the solution part. So yeah, so I think you have, I think you can just come up with this problem is gives you a feeling of binary search because things are repeating here in a like monotonic fashion. So if you observe a pattern, so the first set of alphabets are of length 26, and the second set of alphabets are of length 2 into 26, and the third set of alphabets are of length 3 into 26, and the fourth set similarly 4 into 26. It goes on like I into 26, and if you take 26 common here, uh, so this forms, if you observe, this forms an AP starting with 1 ending on n. So the sum of this AP would be like 26 into n by 2, 2a plus n minus 1 into d, and a is 1 here. So yeah, so if so you can basically binary search on this pattern, and so n is given on the problem, so let's take this as m. So m here is the like last position, imaginary last position of this pattern. So yeah, so we are given n in the question, which is position to be find. So we can basically binary search on this pattern and find a last position whose sum is greater than n. Whose sum is greater than n. So if you observe the pattern, it will be something like for the first set of alphabet. So suppose n is like 64, n is 64. So for first set of alphabets, it will be false, and for the second set of alphabet, that will be of length like 56. It will be not. Let's take something even bigger. Let's take 100. For the first set of alphabets, it will be false, like 26 is not bigger than 100. And if we include the second set of alphabets, it will be 26 plus 2 into 26. So that will be 26 into 3. So it will also be less than 100. So it will be false. But if you include the third set of alphabet, it will be true. And for all the next value, it is always going to be true. So can you observe a monotonic fashion here? So whenever you observe this, you can just do a binary search on the pattern and find the answer. So let's move on to the implementation part. So yeah, this is implementation where I basically inputted n, and this is a base case when it is like less than 26, and you can straightforward answer, print the answer. Else you can like take L is equals to 1 and R, it could be any random value. I took this as 10 to the power 12, which gave me a wrong answer because of overflow. So I basically did hit it and tried multiple R values of R, and 10 to the power 7 sticked. So as I said, I wasn't paying much attention. So yeah, I should have given it some thought and calculate R like precisely. But yeah, so the type of binary search we are using here is binary search. Like I forgot the name, but we use this kind of binary search when we are doing binary search for answer. But this is not binary search for answer. But I like this kind of approach. Basically, in this approach, one of the L or R or R, one of the L or R could never be your answer, and the remaining would be your answer. So in this case, one will never be L is equals to the first set of alphabets will never be your answer because we have included them in this base case. So we can safely take L is equals to 1, and so the position which is greater than n will be stored in R. So L plus 1 is less than R, the mid position, and this is basically the sum. Uh, this sum, this sum, and if it's greater than n, you update R. If it's not, you update L, and now you can just like this is pretty standard stuff. You can think about it and print the answer. So thinking about binary search was important, was like the crux of the problem. So you can, whenever you see a monotonic behavior, anything related to increasing function or decreasing function, anything related to true true true, false false false, true true true, or true true true, or false false false, so you should definitely think about binary search. And yeah, that's pretty much it about this problem. We should move to the last problem, which was the trickiest problem of the entire contest. It took me an hour to solve this, and yeah, so it was you should probably pause the video and think about it. And I'll also explain the problem statement quickly using examples. So I hope you read the problem, and let's just understand it. So basically, you are given a group of people, random people playing rock paper scissors. They are sitting in a circle. So like they have created a weird tournament out of it. Like these people are weird. These people in this coding contest are weird. They need to see doctor. They do weird stuff. Makes our life difficult. But yeah, that is what it is. So yeah. But let's get back to the question. So these people are playing rock paper scissors, and they have shown their choices to like each other. So let's take this example. So the first person has paper, and the next person has rock, scissor, and paper. And so basically, the alternate people are going to compete, and you need to make sure that there are no competition ends up in a tie, and you need to find the minimum number of changes you need to do in this sequence so that there are no ties in the problem. And one thing I would like to mention here, that they are sitting in a circle, so the last person is going to compete with the first person. So the last and the first could not be same. So if you break down the problem, you just need to basically you need to find the minimum number of changes so that all the alternate characters are different in the sequence. So you should like in this example, you will need to, if you change this S and this P to R and S, you can see that there will be no ties, and the minimum number of attempts, like minimum number of changes you will need to do it is 2. So the answer of this is 2. And in the last case, all of them are already different, so none of them ends up in a tie. So the answer is 0. So you should probably pause the video and think about a solution, and I'll discuss the solution later. So yeah, I hope you pause the video and think about it. And so let's discuss the solution. So this problem is basically known called Untie, and I actually don't know if I'll be able to explain it clearly because I used 3DDP to solve this problem, and I'm not sure I can explain it because it involves a lot of subconscious mind to come up with a solution for a problem like these, and I'm not sure I can find words to explain it. Like this is part of the reason why I make this video. I like to explore my subconscious mind. So yeah. So let's just take the first example maybe. Uh, so so let's define the state of DP. First of all, how like intuition for DP, why we are going to use TP. So whenever you need to minimize something, and like the smaller state depends, the larger state is dependent on the smaller state, so you can think about DP. So I thought about it using greedy too, because I think it was I thought it was an easy problem, but it turns out you cannot solve it greedily. So you need to do something with DP, because as I said, you need to minimize the answer, and the states are dependent on each other, like monotonically, like smaller, like largest are dependent on smallers. So you can use DP. So that was intuition for DP. So now let's define the state of DP. Of DP. So I hate this extension DP. So the first state will, as usual, it will be about the index of the string we are at. So let's take like let's say this position is I. So the first state will be uh, the index of any index. Let's say like let's take it I, and the next position will be the character we are going to put at that position. So character C, and the last position is the position for what I was talking about, the subconscious mind involvement. I don't know why I how I came up with this, but I just came up with this. So this is basically the last character we are going to put it. I will try to explain why the storing last character is important, but yeah. So like this state represent the minimum number of changes you will need to make so that the up string till I is idle, like minimum number of changes you will need to make so that there are no ties till the position I with ith character being C, and the last character of the string being last char, whatever. So this is basically the state of DB, and now you will need to think about transition. Thinking about transition is easy. So like DB I C L is equals to minimum of DB I C1 L, when where C1 is among R S P but not equal to the cth character. So if the ith character is S, the I minus 1th character cannot be S. It could be R and P. So this is basically the transition. And yeah, the transitions were quite easy. So let's just move on to the implementation part. I implemented it in Java. So yeah, I basically maintained a DP with the first character up until 10 to the power 5, 10 to the power 4, and the second position is source character, so we only need three positions, 0, 1, 2, 3. 0 represent R, and 1 represent P, and 2 represent S, and the last position is also same, RPS. And yeah, here we are going to just initialize the DP so that we can use it in the recursion. And I used memorization in this because using memorization is easy. It doesn't take much effort. So yeah, so I use this random function which basically returns the state of DP, where S is character, I is the ith position, and J is the, let's just write it, I is the position, J is the character we want at the ith position, and last is the character at the last of the string. I'll explain why this is important. So I did this. I did like simple transition here. There's nothing fancy over here. I traversed over the 0 1 0 1 2. When k is not equals to j, we will just math.min our answer, and yeah, and return store the dp and return the answer. And at the end we calculate the minimum of all when uh, when like we calculate the minimum of dp at nth position when it store r, p or s, whatever is the minimum, we return that in the answer. And now let's see why I used last pointer here. The like storing last is important because in dp we move from a larger state from our smaller state. So if you are moving from like n, when I is n, you are going to move to n minus 1. And in a dp manner, in a tree manner, uh, like uh, I'm just writing this for easy explanation, but you understand how dp works. And now n minus 1 to n minus 2, and eventually you will go to the first position. And storing the ith position, the last character is important because the first character cannot be same as the last character, because if it is same, then those two will result in tie. So I thought about it. I thought about some other kind of memorization. So like storing, I can maybe use some other array to store those, but it wouldn't work. You can think about it yourself. It wouldn't work. You will have to add another state in the DP, and it doesn't do much harm because it's only of length 3. So yeah, the time complexities of this problem is not very much. It's linear, I would say. And yeah, that's pretty much it about this problem. I think did a good job explaining it. Maybe. Yeah, so that was my experience of Code Gym. It was a good round. And yeah, I didn't know that other rounds were happening at the same time. So I would have participated in a harder round because participating in a harder round are better. But yeah, I participated in this, and this was it. So yeah.